Let us look at the tangent and its properties. Consider circle with center O. Let line XY be the secant of the circle intersecting circle in the points A and B. Imagine that the secant XY rotate about A intersecting circle at B1, B2, B3, B4 and so on. Thus, we observe that the length of the chord after certain stage becomes smaller and smaller, and ultimately the secant XY attains the position of the line XY when it becomes tangent to the circle A. Thus, a line in the plane of a circle which intersects the circle in one and only one point is called a tangent of the circle, and the point of intersection is called the point of contact. Let O be the center of the circle and line AB is tangent to the circle at point P. Let Q be any other point on tangent AB. Draw OQ and OP. We see that OQ is greater than OP. Therefore, P is a point on the line AB which is at the shortest distance from the center. Look at the theorem. A tangent at any point of a circle is perpendicular to the radius through the point of contact. Given line L is the tangent to the circle with center O at the point of contact P. To prove that line L is perpendicular to segment OP, let us prove this by contradictory method. Proof. Let us assume that line L is not perpendicular to segment OP. Let us draw perpendicular from O to the line L at the point B such that OB is perpendicular to line L. By assumption, the point P is distinct from B. Let Q be the point on the line L such that P, B, Q are collinear. PB is equal to BQ. Consider triangle OBP and triangle OBQ. Segment OB is common side to both the triangles. Therefore, segment OB is congruent to segment OB. Angle OBP is congruent to angle OBQ because OB is perpendicular to line L. By construction, segment PB is congruent to segment BQ. Therefore, triangle OBP is congruent to triangle OBQ by side angle side test. Therefore, segment OP is congruent to segment OQ by congruent sides of congruent triangles. Therefore, OP is equal to OQ. Therefore, point Q is also on the circle and point Q is different from the point P on the line L. Intersect the circle in two different points P and Q, which contradicts the definition of tangent. Therefore, our assumption is wrong. Therefore, line L is perpendicular to segment OP. Hence, a tangent at any point of a circle is perpendicular to the radius through the point of contact. Let us prove the converse of the theorem. The line perpendicular to a radius of a circle at its outer end is tangent to the circle. We are given that O is the center of the circle and OP is the radius, and line L is perpendicular to the radius OP at the point P. We have to prove that line L is tangent to the circle. Proof. Let Q be the point on the line L distinct from point P. Join OQ. Therefore, triangle OPQ is a right-angled triangle and segment OQ is hypotenuse. Therefore, OQ is greater than OP. That means that OQ is greater than radius. Therefore, OQ is not equal to radius. Therefore, point Q does not lie on the circle. No point of the line L other than point P lies on the circle. P is the only common point to L and circle. Therefore, Line L is tangent to the circle at the point P. Hence, the line L is perpendicular to a radius of a circle at its outer end is tangent to the circle. Let's look at the activity. Draw as many tangents as possible to a circle and find out how many tangents can be drawn to a circle and why. We conclude that we can draw infinite tangents to a circle because there are infinite points in the plane of a circle equidistant from the center. Now draw part of tangents which are rays having initial points, the point of contact on the circle. Also maintain the same direction. What do you observe? Is your figure look like a bhuchakra?